Hello, thank you all for coming to this session on parallel computing and parallel programming. My name is Dori Exterman. I'm CTO at Incredibuild. And before we delve into this presentation, I wanted to give you a short preview on my motivation on composing this presentation. As CTO at Incredibuild, I'm frequently contacted by architects, group managers, and developers that want to scale and increase the performance of their applications. The reason that they contact me is that Incredibuild is a distributed process platform. This means that Incredibuild can take any task, and instead of executing it on your local machine, it can execute it elsewhere, on a different machine, on a virtual machine, or in the public cloud. This effectively transformed a laptop that has 8 cores to a supercomputer that has hundreds of cores and hundreds of gigs of memory. So applications that require more performance and more scalability, they want to use this kind of solution for that. While I speak with these people, I frequently see that there is a lot of information that is missing, and a lot of time they do not take the time to consider which kind of method is best for their application. I looked at the web and tried to find out some kind of document that details the differences between parallel computing methods. Usually it's either multiprocess or multithreaded, but I couldn't find one. So I decided to take the time and to summarize the experience I have from meeting with various companies, various applications, and to assemble some kind of outline that allows developers to understand which kind of method they want to have for which kind of scenario. And I think that before you start writing your application, if you want to benefit from multi-core, you should really take a look at the list of considerations before you start developing. Because when you start, usually this problem is small. You don't know exactly where your application is going to be in the future. But this is where you want to have the most, the amount of thinking made. Because when your application succeeds, and usually the problem grows, this is where you meet the scenarios in which you want to have better performance or better scalability. So in this session, we are going to cover the considerations and the differences between multiprocess and multithreaded. We are going to discuss the pros and cons of each of these methods. And we are going to outline different scenarios, different kinds of applications to understand which kind of method is the correct one for which kind of application. I want to start by giving a very short preview on Moore's law. So Moore's law is something that was with us for a long time. Moore's law essentially says that the processor power will be doubled every 2 years. This was true for a long time. So usually developers said that, okay, if my application or my process is not fast enough, I will wait a year or so, and then the processor power will be doubled and my application will run 2 times faster or something like that. But this law is going to end pretty soon. And the way that vendors coped with that, and as you can see here, vendors started looking at solutions to address to this problem of clock time reaching its limits. And the way that they coped with that is by introducing multiprocessors. So everyone today has 4 cores, 8 cores, 16 cores machine. But as opposed to before, when we relied on the processing power, if you want to benefit from multi-core today, you need to write your application in a way that can benefit from multiple cores. It's not enough to just write your application as is. There are means to really write a good application that can actually take benefit of this multi-core technology. So we will start at covering the multithreaded method. So what are the pros of multithreaded? I think that one of the major points that is a pro for multithreaded is the ease of communicating between threads. So all the threads are, they reside in the same process space, and hence they can communicate with one another either by variables, data structures, classes, and it's easy to communicate both between the threads and between the thread and the parent process that executed them. Another advantage of multi-threaded applications is when you have very large data sets. You have a lot of data that you want to bring to the memory, and then all your threads are working with this data. In this scenario, it makes sense to have all this data loaded to the same process space, and then your multiple threads can access this data very fast and without any hassle. Another thing is that one of the things that you usually need to cope with when you have multi-threaded applications, and I'm not speaking about a single-threaded application, a process which has one thread. In this session, I'm speaking about a process that has a lot of threads, hundreds of threads, dozens of threads, is that when you have threads communicating with one another, or especially when they are writing to the same data structure, you want to avoid collisions, you want to avoid race conditions. And in order to do that, there are a lot of pre-made libraries that allows you to do that. There are pre-made libraries that allow you to have data structures which are thread safe. They encapsulated a lot of classes that allows you to have thread safe out of the box. And essentially, there are a lot of methods that allow you to easily and quickly program multi-threaded applications. So what are the cons of multi-threaded applications? One of them is that when one of your threads crashes, it will crash your entire application, which is not good, and we want to avoid that. Another one is that multi-threaded applications are very hard to debug, especially if we have a lot of threads running in parallel. If we are used to use the debugger, if I just place a breakpoint in one thread, it will stop the other threads as well. And then I'll need to go back to the, if I don't want to have that, and if I want the other threads to keep working while I debug my thread, I'll need to go back to the old logging style of debugging my application, which make it more challenging and more time consuming. Share data. If you want to share data between threads, you need to maintain various kinds of locks, whether mutexes, semaphores, and others, in order to make sure that your threads will not write to the same data both at once. And this is quite complex. So usually, one of the things that you need to consider if you're going multi-threaded is whether you have this kind of scenario. If you have a lot of synchronization, a lot of writing to the same classes. And if you do, you need to consider also the developer is going to implement your application, because a newbie developer can write a multi-threaded application, but it will be more difficult. And usually, even if it's achieved, it can be more difficult to maintain, and it will cost you more than the development. The maintenance can cost you more than the development itself. If we have too many threads, we can waste a lot of time context switching. If I have hundreds of threads in my process, and all of them are living at the same time, the processor will need to swap between threads. And it will waste you some time that can go to computation. So this is also something you need to consider. And the last thing is that threads as an element are not something that you can scale. You cannot take a thread and run it elsewhere. You need to have the minimum atomic unit that you need to have in order to be able to run it elsewhere is a process. So I have scenarios with customers that had multi-threaded applications and they wanted to take a thread and run it elsewhere, and they needed to go back and construct some kind of process that executes this thread in order to be able to have an element, a minimum element, that they can run on a different operating system. So, multiprocess. When I'm speaking of multiprocess, I don't mean that we only have processes. So the scenario that I'm describing here is having a single process that spawns hundreds of threads, for example, or having a process that spawns a lot of other processes. But the processes that this main process spawns, it doesn't mean that they are not multi-threaded. So when I'm speaking about multiprocess, these multiple processes can be multi-threaded. But instead of, for example, having one process that spawns 1 million of threads, I can have one process spawning 1,000 processes, and each of these processes will spawn 1,000 threads. So this is more or less the scenario that I'm describing. So these processes, when I'm speaking about multiprocesses, it doesn't mean that these processes can't have multi-threaded implemented within them. So processes, if a process crashes, it will not crash your entire application if you wrote your application correctly. As a matter of fact, in Incredibuild, a process crashing is a valid scenario, because Incredibuild does not execute its own process only, it also executes the user's process. It takes the user's process and execute it on a different machine. And this process can crash. I didn't write this code, the user wrote it. So it can crash. And I want to be able to recover from that scenario. So in Incredibuild, it's very easy. We know that the process crashed somewhere, either on the local machine or elsewhere, and we simply re-execute this process again. So this is something you can recover from. It's much easier to debug, but in order for it to be easier to debug, you need to encapsulate your process. You need to make sure that your process is independent of other processes as much as possible. And then instead of debugging the entire application, if you chose multi-threaded, so instead of debugging the entire application and just waiting to reach the point where the specific process was spawned, you can simply debug an atomic process, which makes it much easier. It's much easier to debug, it's much easier to maintain, it's much more encapsulated. And one other thing is that it is more easier for team development, because you can have different people working on different processes and they will not intervene with one another. So it's much easier in large groups. If you encapsulated your process well, you'll have less locking issues. If the process has all the data that it requires in order to work properly, you don't need to have any locking mechanism, because no one will override your data, which makes it much easier to develop and very, very much easier to maintain. But it really depends on the requirements that you have, and it's not always feasible. And the last thing is it is scalable. You can take a process using today's technologies and you can offload it. You can offload it to other machines, you can offload it to the cloud. And if your problem grows, if you want to try and solve a problem, for example, transient analysis problem, statistic problem, something else, you can take these processes and distribute them elsewhere. So the drawbacks of multiprocess is that if you do require communication between processes, you have the ways to achieve that. We have a lot of things today that allow us to achieve communication between processes, whether TCP/IP, shared memory, and other stuff. But it takes more time. You need to write your own custom code in order to achieve that. And it will cost in terms of performance. I want to emphasize here, and maybe I'll delve into that a bit later, if you have all your processes being executed on the same machine, and you do need to communicate between processes, you can have something which is called shared memory. Does anyone know? Anyone did shared memory? Great, okay. So just for the sake of people who didn't, you can have a memory reserved for you on the machine, and all these processes can access this memory. But in order to do that efficiently, you need to write your own custom code. You need to make sure and maintain locking between processes. And you should usually encapsulate it. You should abstract this shared memory in order for the developers to be able to easily access this memory from the code that they write within their processes. This is not an easy solution, but it is very, very fast. It's the fastest solution for processes to communicate in the same local machine. The other con is that you don't have a lot of libraries that allow you to have something like process-safe mechanism or some other things that can be shared between processes. So these are the main things that I would like to discuss, and I think these are part of the considerations you need to take. How much synchronizations do I have between my elements? And when I say element, it is before we decided whether this element is going to be a thread or it's going to be a process. So how many synchronization? Are my elements communicating a lot with one another? Do they have a lot of data that is shared? Do they write to the same kind of data? How does it work? What's the size of the data I'm expecting to have? And this is one of the things that you really want to consider at the beginning, because one of the things that I see a lot with my customers is that they started with very, very small sets of data. And once their product succeeded and was successful, and more people started using it for more scenarios, the amount of data just increased. And then their problem just grew, and then it took more time to solve. The solution took more time to execute. And this is something you need to know in advance for the future, because if you do not consider that, once you'll have this kind of data in the future, it will be very, very hard to maintain your application, and you need to do a lot of re-architecturing in order to support that. Who are my team developers? Are they newbies? Are they expert? What can I expect from them? And scaling. Do I see any possibility of scaling in the future of the application? So let's delve into each one of them. So synchronization. If I have a lot of synchronizations between my elements, let's say, for example, artificial intelligence. Artificial intelligence, you usually have a lot of threads, and these threads communicate with one another, and they communicate a lot, and they communicate very rapidly. In this case, usually multithreaded is something that you want to consider. It's easier to debug, as I said, multithreaded in some scenarios. In multiprocess, if you want to have synchronization, you will need to have custom development for that. And many mechanisms exist, both for multithreaded and multiprocess, to do this kind of synchronization. So you have TCP/IP, UDP, broadcasting, you have databases, you have files, you have shared memory, so you can do that. But if you have a lot of that, multithreading can be very, very easy for this kind of applications. So ease of development. As I said, there are a lot of pre-made libraries for multithreading. But in multiprocess, if you can encapsulate your process properly, and if every process has its own kind of data, it will be much easier for you and less costly to maintain. requires the developer to do a very good encapsulation on the process in order for you to be able to achieve it. And it can be maintained, if you have multiprocess, it can be maintained by less experienced developers. And if your process is well encapsulated, bugs are usually much easier to solve than in multi-threaded applications. How many of you have ever had some kind of race conditions between their threads? So I see smiles. So this is a real pain, right? In order to solve a race condition, it can take days. And there are race conditions that you cannot easily detect and you cannot easily solve. In multiprocess, if your processes are well encapsulated, this is somehow a rare scenario. Another point I wanted to bring out is the throughput. Throughput means how many tasks, elements do I have to spawn, okay? So if we have very, very few, if I have 1, 2, 3 elements, then I think that the question is less complicated, okay? It really means you need to take less time in order to consider actually what it is that you want to do. But if you have hundreds, thousands of elements, this is very, very meaningful. So how many tasks do I have? And how many tasks will I have in the future? Okay? How much time will it take my tasks to execute? If my task takes something like 2 milliseconds, spawning a process for each of these tasks is not very, very smart thing to do, because just initializing the process and then destroying it will take time. In a scenario that I have with a customer, they have millions of tasks, and each one took a few milliseconds. So spawning a process for each of these tasks is not smart. But what they did, for example, is they packed together some hundreds or thousands of tasks, and a single process executed 1,000 tasks. And then you have a process that takes a few minutes. And that starts to make sense. Okay? That starts to make sense. If a process takes a few minutes, the initialization time of the process is not that meaningful. How much memory will my task require? So if every task that I have will require a very significant amount of memory, I can reach some kind of limit. And then I will meet some kind of swapping, and maybe I'll exceed the memory limit of my process space. And this is something you need to consider as well, especially when you want to think about the future. And the last thing here is how large the data that each task will require. So in real-time systems, in real-time applications, you usually need to get your data and calculations done really, really fast. So you don't even have the time to wait for initializing a process. Usually in real-time application, you'll use multi-threaded. Another thing that you want to consider is scalability. In the future, or even now, can you benefit from scalability? And scalability means you can spawn more and more, you can use virtual machines, remote virtual machines, you can use the public cloud. And one of the things that you want to understand here is that it also have business implications. So one of the things, the cloud, as you probably know, is one of the hottest thing today. And when you have the ability to scale to the public cloud, this has a business value, because then you can sell to your customers some kind of enterprise model. You can sell your product as a service or extend some services to your product, which make it much more interesting in terms of business value. There are other things you need to consider. For example, if your tasks require special hardware. If your task requires special hardware, it can be very costly. If you want to sell your application and your application requires special hardware, it means that your end user will need to pay more for your application, because he will need not only to purchase your application, but also the special hardware in order to execute it. But in a lot of scenarios, only a small portion of your application requires special hardware or can benefit from special hardware in terms of performance. For example, GPU. There are some scenarios in which GPU is the best solution. There are problems that GPU can solve so much faster than CPU. But a lot of times, this is just a small portion of your application. So for example, if I have a very large application, does a lot of stuff, but as part of my application, I want to do some, I don't know, password decryption, okay? Password decryption is something which is very, very good for GPU, okay? So if I can break this problem and say, okay, 90% of my application will run more or less the same on CPU or GPU, but 10% or 20% will run very, very well on GPU, very fast. The thing that I can do here is that this 20% can be executed as a process, as a different process. And then I can take this process and offload it to a machine which has a discrete GPU card. I don't know if you are aware of how many are aware of Tesla, for example. Tesla has hundreds of cores, GPU cores in a card, and it can perform very, very, very well for specific problems. So you can have a single machine with a Tesla or some other GPU card, and you can have a lot of users, and just the portion that will run much faster on the GPU, you can scale and distribute it to this specific machine with the GPU card. And your entire application will run much faster, and you will also cut costs for the user because he can share this special resource for a bunch of users. And also you need to consider connection with the database. So if you have multiple threads, it's quite easy. You have some kind of connection pooling, and then you can decide how many connections you want to have. But if you have multiprocess, usually you'll have a connection per process. And if you have a 64-core machine and you want to execute 64 processes, you need to make sure whether maintaining 64 database connection is something that you want to have. So I want to delve into a concrete scenario. In order to delve into that, I chose two applications. Each one took a different method to solve the same problem. We have Maven and Make. These are both build tools. Probably most of you are familiar with Make. I believe that less maybe are familiar with Maven. But they are both compiling code, very similar in terms of what it is that they are doing. Maven is multi-threaded, while Make is multiprocess. The reason that I chose a build tool for this example is that these are very common. Both of these tools are very common. They try to solve the same scenario, and they have millions of users that use them daily. They both started quite early, several years ago, and when usually you had only a single core in your machine, okay? And we can see how the problem developed after a few years. They have many tasks. For example, compilation tasks. You have a lot of compilation tasks. Each compilation task is usually atomic. It doesn't require much. It does not depend on other compilation tasks, okay? They have minimal communications, small data sets, only a CPP file, H files, things like that. It's a very small data set. And there is the potential of scalability. So let's see how each of these applications coped with changes of time. So, as I said, Maven is multi-threaded. In fact, it was single-threaded just a few years back, and they just made a progress and made it multi-threaded, which is very nice. But still, you are limited to the amount of processing power you have on your local machine. So I don't know if you can see the small letters here, but these are forum posts which complains about the time that it takes to build large source codes with Maven. People are saying, okay, there are distributed solutions, but Maven cannot be used for that with them because it is a multi-threaded solution and you cannot distribute the thread to a remote machine. And there are also memory problems because code began to be larger and larger, and sometimes you need to have more memory than the process space could allow you to have. So this is how it looked like when you had a single core, but when Maven implemented multi-threaded solution, you could use your entire laptop. So this is a print screen from Incredibuild. I couldn't use my laptop, so I can't show it to you live on the monitor, but we will need to, it will need to be enough. So on the left side here, just for you to be able to understand what it is that we are looking at, these are the cores of the machine that are currently executing the tasks, the compilation tasks of Maven. And each bar here represents a task, whether a compilation task, a linking task, some other execution. The scenario that I'm showing here is Qt. How many of you are familiar with Qt, the very, very popular UI? Yeah, okay, great. So as you can see here, this is much better than it used to be before, but still it is quite limited. So today, a lot of times in the open source, open source is very, very common. And we have customers that are not just building their application, but they also made some changes in the open source that they are using. And they also need to compile these open source libraries. And compiling these open source libraries, which grow and grow over time to give more benefits and more scenarios, to cope with more scenarios, it takes a lot of time. This is a scenario that you didn't have in the past. 10 years ago, you didn't have this amount of open source that you wanted to compile as part of your application. But this is not true today. So if someone needs, as part of his application, to recompile Qt and recompile Boost and recompile Ace or things like that, it can take a long, long time. And this is why people are complaining. Another thing, okay, so let's continue and then go back. So Make chose a multiprocess method in order to implement the build problem. So it has much better memory usage because each process has its own memory space, and it is scalable. There are third parties that can scale the build. They can scale it to different machine. They can distribute and offload the task to different machine, which allows you to have much more cores than you have on your local machine. Another thing is that these kind of tools can also go inside and see whether they can run your processes in a better way, okay? Whether they can find some dependencies that you think that they are there, but they are not. Okay, let's take a look at the previous slide. As you can see here, we have here some executions that occur only on a single core. Each one of these tasks probably depends on the previous one, but in fact it does not. That's only the way that Qt implemented their make file, okay? Now, with a third-party solution, such as Incredibuild, as you can see, these mock files are being executed in parallel. Because Incredibuild detected they are not really dependent on one another and can be executed in parallel. So although Make is the one spawning these processes, a third-party tool can intervene and can say, okay, so I know that these are not, this can be executed in parallel, and I would like to execute it in parallel. And due to the fact that there are processes, the third-party tool can actually intervene and execute them in parallel, as opposed to multi-threaded. So in Maven, no one can go inside and decide to spawn these threads in parallel because you cannot go into this kind of level of granularity. So this is only a benefit you can have with multiprocess if your application was developed in a multiprocess manner. So again here, we have 8 cores, and it's more or less, besides this optimization, it's more or less the same. It's 30% faster, but still more or less the time that it took to run with Maven. Okay, and if I didn't have this optimization, Make and Maven will execute Qt more or less at the same time. Maybe Maven will run a little bit faster due to the multi-threaded. But with multiprocess, you can then scale. What we're seeing here, this is the local machine. And in the local machine, I just want to execute tasks that I want to execute in the local machine. For example, linking. Linking requires a lot of OBJ files, okay? It requires a lot of data. So I prefer to run linking on the local machine instead of transferring this data to the remote machine. But all the compilations, which requires a very small amount of data, can be distributed. So as you can see here, this is one machine, and these are cores from other machines. And the compilation tasks are being distributed to these machines. I'll just go another slide, and you can see more of this list of machines that are currently participating in the Qt build. And as you can see here from the scroll bar, I have much more machines that participated in the build. In fact, this was executed on several machines. All of them are 8 cores machine, and it accumulates to 130 cores on which I execute my Qt build. So instead of finishing in 15 minutes, I can conclude my Qt build in 1.5 minutes, which is very, very meaningful. Okay, some real-life scenarios. My aim here is to give you some scenarios of applications and the way that they chose to implement the parallel computing, which method they had. So let's start with application which have large meshes, large data. So we are speaking about CAD application, artificial intelligence application, weather forecasting, genetic algorithms, things like that. You have very, very large data sets. You want to have all of this to the memory, and the threads are just communicating with one another and with the data. Usually, this is a multi-threaded scenario because you cannot break the data to be executed in multiple processes. You don't know which part of the data your element will require. There are scenarios in which a large data can be broken. For example, we'll show it later. For example, rendering. Okay, I can have a very large data set to render an entire movie. Okay, but instead of rendering a 90 minutes movie, I can render 1 minute per 90 parallel 1 minute movies. Okay. And I can break this data because I know the data that needs to be generated or gathered for each specific process. In weather forecasting, you do not have this kind of information. So you need to have all this data, and all the elements that you have need to communicate, and you don't know which kind of data they will require. So this is a multi-threaded scenario. Real-time, financial transaction, defense systems, these are scenarios in which you need to have very, very fast feedback, usually milliseconds. And as we said before, these are not scenarios in which I want to have the overhead of spawning another process in order to do that. So this is also latency, initialization time. This is also a multi-threaded solution, usually. There are scenarios such as in CRM, ERP, SAP, for example, which most of the business logic, most of the calculation is done in the database. It's not done by your application. If you have a scenario which most of the data is done in the database, and the only thing you need to do is to take this data later on and just present it or do some kind of very minimal calculation with it, usually a single process with maybe various threads is a good enough scenario. This can change if you suddenly have scenarios in which you have much more data and much more processing on the data in your application. So for example, if you have a large data set that you get back and then you want to calculate things, then a multiprocess scenario can be something to be used in these scenarios as well. So When we have high throughput scenarios, which kind are relevant for multi-threaded? So if we have a simple scenario, for example, I just have 1, 2 threads doing very small stuff, or even a few more threads, I don't think that having multiprocess, unless you really can encapsulate them very fast and you want to enhance your maintenance, so usually a multi-threaded is kind of natural. Long initialization time, real-time, communication, syncing, and if you only have a few highly intensive tasks and you don't see any foreseeable future that you'll have more than that. Okay, so now we'll go into multi-process scenarios. This is also, as I said, these are also large meshes, large data sets. But as I said in rendering, these can be broken. So I give the CAD solution. So there are solutions in large meshes, for example, transient analysis, when you need to analyze a lot of data. So in transient analysis, most of the application that implemented transient analysis did it in multi-threaded fashion. But there are few who took the extra work and extra time to implement it in a multi-process way. This means that they needed to understand exactly which kind of data will be needed by which kind of element. So for example, ANSYS, which is a very, very popular company, PSCAD, they broke down their elements instead of multi-threaded to be multi-processed. These kind of problems can take weeks. So in PSCAD, it takes, for a large mesh, it takes 2 weeks to solve a problem. For example, they handle national electricity in Canada. So if something goes wrong with the power plant, how will it affect the entire national electricity system? These are problems that they can take weeks to calculate. And with multi-process, with multi-threaded, there is nowhere you can go except purchasing better hardware, but still you'll be stuck to something like 64 core, 122 if you are going hyper-threaded. This is not enough. So instead of 2 weeks, it will take 1 week. This is still a long time to wait. So the companies that took a multi-process approach were able to benefit from scaling. They were able to benefit from thousands of cores, from public cloud, self-services, things like that, in order to both solve the problem much, much faster, because these are usually things that you can run independently, and also provide added benefit in terms of business, both to their customers and for their companies, okay? Because when you start selling services or software as a service instead of just selling your application as a box, you can get much more money and much more, connection with the customer. Financial derivatives. We have a lot of customers using distributed computing, multiple processing in financial derivatives, calculating end-of-day information for papers, for example, in NASDAQ or S&P, okay, or stock market. So these are very independent data sets. Every stock has its own data set. So this is very, very natural to divide the data sets, and then you have each process just calculating a single paper with the data set of this single paper, this single stock. Okay, so financial derivative simulations, very, very large data sets, but it can be easily broken into smaller data sets. Rendering, we already spoke about, and there are a lot of different scenarios in large data sets that can be broken. So multi-process, I believe, is better for this scenario as well. There are scenarios in which we have very small data sets, and the elements are independent of one another. So these are compilations, testing, code analysis, packaging, encryption, decryption, things like that. This is classic multi-process as well. We spoke about GPU a little bit. So GPU is usually used as a multi-threaded due to the nature of the way the GPU works. But you can have also multi-process for that if you want to offload some processes to a concrete GPU card, as we discussed before. And it means that they will run much, much faster, and you'll allow your customer to spend some money in a specific GPU concrete card, and it will be shared with all the users. So each of them can finish his simulations or execution much faster than it can on his local machine. Streaming. Streaming is very popular today, and also this is classic multiprocessing because you want to service a lot of users. So if I have millions of users, I cannot have a single application spawning a thread per user. I may have tens of thousands of processes, each one has a couple of threads, and it can, it can service a few users, but essentially this is a classic multiprocess as well. And combining that with the public cloud is what we have today when we're using streaming services, live game services, and things like that. And last thing is cloud. If you have the ability, as I said, to spawn processes, to distribute them to remote machines, to the remote cloud, you can start selling services. And if you take a look at Microsoft, which changed the entire focus of the company from being an application-centered company to a services and mobile company. And you can see a lot of other large companies as well going towards this kind of services. So if you can have your application providing your customers this kind of services, you'll be able to get a better business opportunity, a better business value. So these are sets of things that we discussed. This is kind of summary. So can my execution be broken into independent tasks? If they are not independent, how much they communicate with one another, how rapidly they communicate with one another, how frequently they do that. If it's not that much, and if I can break my execution into multiple processes, multiple elements, this is always something that you should consider doing. And if your work can be also divided between multiple hosts, so you have very large, it takes a long time to compute your solution, you really should consider multiprocessing because that's the only way you can benefit from other resources, other machines across the network or the cloud. The amount of data I have, whether I can break the data or I cannot break the data, whether I need everything in memory or I can just load a bunch of it, just part of it to the memory, these are things you should consider. How many relations do I have in my database? Whether my tasks can run in parallel or are they dependent on one another? And if they are dependent on one another, whether it has to stay like that, or whether I can have some tasks depend on one another, but the others can run in parallel. This is very meaningful when you start architecturing your application and not after you developed it. And this is usually where the problems go. As the application was developed for a very small solution, and then it starts growing, and you start having more and more users, and then it's a bit too late to do that. So we've spoken about communication, the complexity of the development, things like race conditions and things like that, and the scaling and performance of the application using clusters, using cloud services, and things like this. There are a lot of solutions today in the market that allow you to have multiprocess, and it just grows. Multiprocess is just the way to benefit from the multi-core technology that the world is going to benefit from the cloud services that the world is going to. We have devices that are that start being, smaller and smaller, and they have a lot of time less resources than we used to have in our PC, and we don't necessarily want all our executions to run in my mobile, for example. If I have a compute problem in my mobile, I don't want all my processing to be done in my mobile if I can prevent it, because then, no one will want to use my application if I'll take all his processing power from his mobile. And if we are going to Internet of Things, this is just the problem is just going to increase because Internet of Things it has even less processing powers than other stuff. So these are the list of considerations that I thought of. This is coming from my experience and things that I've found in the web. But as I said, this is something for the community. I think that I didn't find any comprehensive list such as this, that someone that begins to write an application can just go over and just go over one by one and see whether this is important for him or not, whether this is relevant for his application, and just try to rethink the way his application is going to be written and maintained in the future. So this is what I wanted to do and provide it to the community. And I'd be happy to hear from you, whether you have questions or if you have other points that I didn't think of, either pros or cons, or just scenarios with which I can extend this list. I'll be happy to hear them. So thank you, and if you have any questions, that's it. Thanks. But only in English, or if someone else can translate, I'll be happy.
Thank you for the lecture. The question is, when you enumerated the pros of multiprocessing versus multithreaded design, one of the points was less locking. How is that?
One of the point was, sorry?
Less locking.
Less locking, okay.
How is that? Isn't it completely a matter of design of the solution instead of...
Yes, you are correct with that. But one of the things that I understood from my experience is that when customers are building their application in a multi-threaded manner, they don't think, they think less about locking. So they just say, okay, I can use a mutex here, I can use a semaphore, and that's it. And they do that. And then you have all these kind of problem coming from that. But when you say, okay, I want to develop a multiprocess application, then you start considering locking much more. And then you can have something like lock-free. I don't know if, are you familiar with lock-free scenarios? These are scenarios in which you can have a lock, but if you just think it through and maybe do some more complex code, you can live without a lock. And this always makes better applications. They perform better, and especially the maintenance part. So this is what I'm referring to. If you do need to have locks in multiprocess application, if they really use shared memory or things like that, it will be as complex as multi-threaded. Not always, but more or less. Yeah.
Hi, thank you for great talk. I wanted to ask, you mentioned that if you have a lot of threads, then we'll waste some time on context switches between the threads. But the context switch between different processes is much pricey than context switch between the threads. So if the scalability in terms of multi-machine scalability is not a question, I think that the inter-process context switch can be restricting for taking multi-process approach.
Yes, I agree with you. What I meant to say here is if you have a lot of threads versus a lot of processes, as I said, if you'll be able to distribute them across machines, you'll have less context switching. But if all of them will be on the same machine, the processor will still be busy context switching between processes in very similar manner to the way it will be with threads. But something else is that usually with processes you have more controls over it. but it really depends on your scenario. So the general answer for your question is yes, you're right.
Okay, thank you.
But in multi-threaded, you won't be able to change it forever. With
Yeah, I get it.
multiprocess, you will be.
Thank you for your lecture. One more question. You said that one of the most major pros for multiprocessing is that you can distribute your application between multiple computers, yes? I think that it's not that easy, because when you actually run your application in multiple machines, that's when all the bad things happen, because it's not easy to control them, especially when they're really territorial distributed. When you have not one, two, three machines, thousands of them, you have to build real complicated controlling application for keeping them together.
Yeah.
And I think maybe you should clarify that moment a little.
Yeah, that's a great question, and I'm very happy you asked it. So if you have multiprocess and you want to distribute, you have two ways to do that. One is to write your own platform to distribute these processes. And yes, it can take time, it can take effort, but that's the only way to solve this kind of problem. With multi-threaded, you don't even have a way to solve this kind of very, very long solution. But, and I think this but is very important, you have today a lot of solutions that do this for you. You don't need to develop yourself the mechanism that distributes the processes. For example, Incredibuild is just one of them. Okay, Incredibuild takes your application. Let's say that you have a master process that spawns 1,000 processes. Okay, you simply execute your master process with Incredibuild, and you will write in a configuration file which name of the processes, the name of the process you want Incredibuild to distribute, and Incredibuild will do that for you. So if you have a simulation application, simulation.exe and subprocess.exe, and simulation.exe execute 1000 subprocess.exe, you simply need to have a configuration file saying subprocess.exe I want Incredibuild to distribute. Incredibuild will distribute it to a remote machine. It will virtualize all the data that this process requires, so you don't need to install anything on that remote machine. You have a sandbox that Incredibuild does for you, and it will also get back all your data to the local machine. So we have scenarios with customers, gaming companies such as most of the large gaming companies such as EA and Capcom, and all the Xbox, PlayStation games, financial companies, CAD companies, and they have already their multi-process application. And they can take Incredibuild and use it out of the box to distribute that. Same thing you can do with clusters. Same thing you can do with Univa. Same thing as you can do with something similar to Hadoop. So you have an infrastructure that is pre-made, and it's an expert infrastructure that allows you to distribute your processes, to manage your machines, that does all the virtualization for you. It brings everything that you need to this local remote machine and brings everything back. It's really as though with Incredibuild, as though you have 1,000 cores without doing anything. So with Incredibuild and with clusters, if you have set the environment, the only thing you need to do is write a command and execute thousands of tasks, and this infrastructure will do all of the things that you are speaking for you. So it gives you the opportunity to do that. So usually, I recommend for customers that don't already have this kind of solution for distributed processing not to develop them themselves, because that's not their main expertise. For example, PSCAD or Sarin is a diamond manufacturing company. They have millions of simulations that they execute. Their expertise is in diamond grading and diamond evaluation. They don't need to have an expertise now in distributed computing. So if you can have a solution that does it for you and have all the management system and everything else as part of it, this is what I'm speaking about.
Yeah, thank you.
Yeah? In the back?
Thanks a lot for your great talk. I want to return to threads. And by the way, often if you have some complex task, you may make the amount of threads equal to your cores. And that's it. Can you please give some viable example when you have really many threads, and it's a real example, just not threads amount equal to number of the cores of the machine? Maybe just example.
So I'm not sure that I understood the question. Are you asking whether I can give an example of a scenario in which I want to execute more processes than I have cores in my machine?
More threads. So you have real extensive usage of threads and context switch problems, but what is a real scenario? Maybe you will give example, because you may have queue of your queries and have 4 or 8 threads each per core. Thanks.
Yeah. So one of the scenarios that I know of is, and I recently had heard a talk related to astronomy, calculation in the field of astronomy, and they are all using a very large data set. Okay. So and they need all. So they don't know which part of the data set the thread is going to address. So they need to have all this data set in memory, okay? So they cannot do multiprocess in this kind of scenario. And each thread compute different, they are speaking about collapsing galaxies and things like that. I didn't get the astronomical part, but each thread just compute something specific out of this large data set. So in order to achieve that, and in order to understand how many threads they can really execute in parallel, what they had is a sampling application that sampled the resource usage of the machine. And once it sees that there is a starvation, which means that the machine has more resources available than you want it to have, they just spawned more threads. And once they saw that the machine started context switching and swapping and things like that, they just didn't execute more thread and allowed the one that in the queue to finish until they saw that they have a starvation again. And then they started executing more threads. So in scenarios where you can execute a lot of threads in parallel and you want to know what's the right number for you, you can either guess or you can write something that will just all the time will analyze the amount of resources used in the machine and spawn these threads according to that. Is this good? Yeah? Great. Anyone else? Thanks a lot. I hope that I helped you.